Okay, so as we were talking about looking for patterns, we recognized that if we multiply 5 to the second power, we expand it and it looks like 5 times 5, which is 25. 5 to the third power, 5 times 5 times 5, that's 125. I took the previous value and I multiplied by 5. To get 5 to the fourth power, I'm multiplying by one more 5. I take 125 times 5 and I get 625. The opposite of that would be to go from 5 to the fourth, 5 to the third, and I'm going to be dividing by the base, which is 5, and I get 125. If I divide 125 by 5, I get 25. That's 5 to the second power. To get 5 to the first power, I'm going to divide 25 by 5, the base, and that gets me 5. And here's the interesting part. When I divide 5 by another 5, that's going from 5 to the first power, 5 to the 0 power, and 5 to the 0 power, 5 divided by 5 is 1. So as the exponent increases by 1, we multiply by a base. And as the exponent decreases by 1, we divide by a base. So now you're going to find the values of the first 5 powers of 3, including 0. And the easiest power to start with is going to be squared to the second power. So 3 squared looks like 3 times 3, and I get 9. And we do this because in case we don't have 3 to the third power memorized, we have a starting point. We can take our 9, and we know we have to multiply by one more base. So 3 to the third power is 9 times 3, and that gives me 27. To get 3 to the fourth power, if I expand it, I can use the associative property and group 3 times 3, and then the other 3 times 3. And that gives me 9 times 9. And we know 9 times 9 is 81. It's a lot easier to work that way than, say, 27 times 3. Now, to get 3 to the first power, I'm going to go in reverse. I'm going to divide 9 by the base, which is 3. And when I divide by 3, 9 divided by 3 gives me 3. So 3 to the first power is 3. It's itself. If I divide 3 by 3 to get 3 to the 0 power, 3 divided by 3 is 1. So, to answer any questions about raising to the 0 power, any number to the 0 power will always equal 1. I jumped a question. Any number to the first power is going to always equal itself. And now we're going to talk about negative exponents, which is so interesting in a geeky kind of math way. So we're going to go back to the powers of 5, and I'm going to actually take this a little further because we've done this already. And I'm going to extend the chart. I'm going to extend it there. Okay, so we know the easiest one, 5 squared. Although now we know that 5 to the first power is really the easiest one, because anything to the first power is itself. And we also know that anything to the 0 power is 1. So now I can just continue on multiplying by 5s. And now I'm going to continue with the pattern of dividing. If I divide 1 by 5, we know that all fractions are actually division problems. And the opposite, or the converse, is true as well. All division problems can be written as fractions. So this is a division problem. 1 divided by 5. And that's what happens when I have a negative exponent. It's not a negative answer. It just gives me a smaller number. So if I have 1/5 and I divide by 5, because that's my pattern, 1/5 divided by 5, we can't divide a fraction by a whole number. I have to make it a fraction. And when I'm dividing fractions by fractions, I'm actually multiplying the fraction by its reciprocal. And 1/5 times 1/5 is 1/25. So 1 to the negative second power is 1 over 25. And I'm hoping that you see a relationship between 25 and another number here. What do you see, Stevie?
Oh, so like in the positives, you just gotta put a 1.
Okay, do you want to refine that a little?
5 and negative 5 with the exponent of -2. The denominator is the same as 5 with positive 2 as the exponent.
So it's a reflection of what the positive exponent would be. The only difference is it's in the denominator, and 1 will always be my numerator. So 5 to the negative third power should be 1 over 125, or 1 over 5 to the third power, because that's what 125 is. I can rewrite it in terms of an exponent. So go ahead and find the first 3 negative powers of 3, and then we'll get our rule down. And you'll be able to pause and go back and write anything down that you missed. So if I had 3 to the 0 power, I know that that's 1. If I divide 1 by the base, which is 3, 3 to the negative first power will read 1 over 3. 3 to the negative second power will be 1 over 9. Just joking. And 3 to the negative third power is 1 over 27. So the pattern or the rule is that negative exponents, when simplified, will be fractions with the numerator of 1, and the denominator is the power without the negative exponent. So you can pause, process. We're going to move on with multiplying powers with the same basis. I think we've established that if we have 3 times 3 times 3 times 3 times 3, we have 5 3's that are being multiplied. And we can write that with the base of 3 and the exponent of 5. But what if I take these 3's and I use the associative property and I group them differently? I have 3 times 3 times 3 times 3, which is 3 times to the 4th power. And then I multiply it by that last 3, bless you, which is 3 to the first power, I still am multiplying 5 3s. I'm just grouping them differently. So 3 to the 4th power times 3 to the 1st power is the same as 3 to the 5th power. If I group them a little differently and say 3 times 3 times 3, which is 3 to the 3rd power, and I multiply that by 3 times 2, it's 3 to the 2nd power, I'm still multiplying 5 3s. So I still get 3 to the 5th power. Do you see a relationship between the exponents? The relationship between 4, 1, and 5? Or 3, 2, and 5? What do you think?
If you add 4 plus 1, it will equal 5, and if you add 3 plus 2, it will equal 5.
Okay, so the sum of the exponents is the total number of bases that I'll be multiplying. If I had 5 to the 2nd power times 5 to the 4th power, if I expand it, I have those 2 5s here, I have 4 5s here, and what that looks like is 5 to the 2 plus 4th power. So I get 5 to the 6th power, and that's how many I'm multiplying altogether. So the rule is, when multiplying powers with the same base, we're going to add our exponents.